Alrighty, so I'm just going to get this out of the way first and say the most generic things. Hi, I'm Savannah, and I'm going to be doing my presentation on luciferin. Now that I got that out of the way, I'm going to go into more detail. Luciferin is the reaction in many creatures that creates a bioluminescence that creatures use for many functions. In the case of fireflies, for adults, they mostly use it to identify their own species and use patterns to attract the proper mates. Going down this little list of mine, the reason why I have chosen my molecule is because I recently discovered a project created by 3 people that states humans actually consistently produce light, not in the sense of infrared radiation, but physical light. And the reason why you can't see it is because the light is so weak, 1,000 times weaker than our eyes can capture, to be specific. And this got me thinking, well, what else lights up? Fireflies. Granted, fireflies make their light in a different way, but in the same thought, we both create light. The way fireflies make their light is by combining oxygen, luciferin, ATP, and luciferase. All this makes this relevant to what I've been learning in class, that things can be the same in one way, but also could have minor differences that can cause different reactions or behaviors altogether, like cis and trans molecules or chiral molecules. For example, I've drawn here is 2 types of butane and thalidomide. The first is trans 2-butane, with its CH3s opposite from each other, and here is cis 2-butane, where they're on the same side. Down below is
Chiral thalidomide.
the one to the left here is
R-thalidomide.
and it reacts in a way that it is bioactive, but the other here
S-thalidomide is
toxic. Just look at this. Such little differences, and they can cause so much danger or help. So, my molecule for fireflies, D-luciferin, can be seen drawn in all its glory. Its molecular formula is C11H8N2O3S2, and using the International Union of Pure and Applied Chemistry, or IUPAC for short, is written like this. As you can tell, this is an aromatic molecule with all these benzene rings within it. You can also notice that at the right end of the molecule, it has a carboxylic acid attached here. And in the middle, 2 secondary amides shown here, and 2 thioethers shown here. At the left end of the molecule, there is an alcohol shown here. In total, there are 6 functional groups. This particular molecule does have 2 types of isomers, and to be exact, they are chiral and an optical isomer. The chiral molecule to D-luciferin is L-luciferin, and like
thalidomide.
the only difference between the two is one bond is going from into the page and the other out of the page. The optical isomer is also called D-luciferin, and the only difference between the two is almost like the difference of cis and trans, but it's not, because one entire side is completely flipped, but neither side is symmetrical. Coming back to D-luciferin, let's look at this at a different style, 3D. Now I can show you the shape of this molecule. The majority of the shape is flat, mainly because of the double bonds sprinkled throughout, restricting it from twisting in the way it wants to be if it were split up into segments. The only shape other than bent with a bond angle of 109 degrees in the molecule is the trigonal planar on the carboxylic acid with a bond angle of 120 degrees shown here. Finishing off my presentation, it's just incredible to learn that there are multiple types of bioluminescence out there, and it's not just luciferin that creates these amazing, natural, bright colors. Just to conclude my presentation, I want to show you a snippet of fireflies doing their thing. I personally just find it so cool what nature can do. Thank you so much for listening to my presentation.